Schema Registry and Protobuf can make your pipeline smarter, faster, and far more reliable. But let me ask you this. Why does JSON break at scale? What is this format that big tech uses to shrink their data and catch schema issues early? And how do teams manage it without constantly breaking their pipelines? At Netflix and Uber, millions of Kafka events flows every second. But at scale, JSON become bulky and error prone. In this video, we are not just going to talk about the theory. We are building a full real-time data pipeline with Kafka, Protobuf, and Schema Registry from the scratch. And in just few minutes, we will dive straight into the hands-on development, building everything step by step. You will learn how to serialize data with Protobuf, register schema live with Schema Registry, handle schema evolution, consume events reliably with Spark, and later we will break the pipeline on purpose to show you how schema compatibility actually saves your system in production. Plus, watch out for the break the system challenge scattered throughout the video. Real world puzzles to test your thinking, sharpen your skills, and maybe even help you crush your next interview. Trust me, the last one is tricky and totally worth it. Stick around. By the end, you won't just understand Kafka, Protobuf, and Schema Registry pipelines. You will know how to build, scale, and fix them like a pro. Let's break this down. Say you are building a food delivery system like Zomato or DoorDash. Every time a user places an order, an event is published to Kafka topic, something like this. This order placed events consumed by multiple streaming systems like the fraud detection system that might be written using Python and Spark, delivery ETA service may be running in Go, customer notification service might be running in some different language like Node.js, accounting and invoicing, maybe that's running in some other language, Java. Each of these consumer parses the same JSON event in their own language. JSON is flexible, human readable, easy to start with. But that flexibility become your enemy in the production. It's verbose. Every field repeat per message. At scale, that's gigabyte wasted. And worse is it's schemaless. If one producer changes a field name or adds a new field, consumer breaks. And debugging that in real-time system is a nightmare. Imagine one day a developer rename customer ID to cust ID. Another adds a new field. A third accidentally changes the type of amount. Now Spark failed to parse the schema. The Go service silently ignores this missing field. Java throws a runtime exception. Dashboard breaks and no one knows why. JSON doesn't enforce a contract. There is no guarantee of what structure is expected. No versioning, no type checking, no warning. You are flying blind. And imagine in large teams, this break things fast. You realize your biggest issue is not Kafka. It's not Spark. It's this. You don't know what your messages are supposed to look like. And your consumers are just guessing. That's when you start thinking, what if producers and consumers agreed on the message structure and the structure was enforced? That's where Protobuf enters in the picture. Okay, so enough talking. Let's see how it works. But before we dive into the demo, here is what we will build. To truly understand how Protobuf and Schema Registry work in action, we are going to build a real streaming pipeline using Spark and Kafka, step by step. The demo will have two main parts, both running as Spark structured streaming jobs. So the step 1, order producer, the serializer. We will simulate an incoming Kafka topic called order This contains the events in raw JSON format, like the one you would get from the production app. Our Spark producer job will read the JSON message from the orders topic, convert them to protobuf format using .proto schema, register the schema with schema registry, and write the serialized protobuf message to a new Kafka topic. Then step 2, order consumer, the deserializer. Now we will spin up another Spark job and that acts as a consumer. This job will read the binary protobuf message from the order serialized topic, fetch the correct schema from the schema registry using the embedded schema ID in the message, deserialize the data back into the structured record, and finally write the output to another Kafka topic. So, by the end of this demo, you will see a full pipeline where JSON goes in, protobuf comes out, and consumer decodes everything using schema registry without ever needing the .proto file manually. Ready to see it in action? Let's jump into the demo. Alright, let's start building our pipeline using Kafka, Protobuf and Schema Registry, step by step. So what do we need? We are going to build both a producer and a consumer as streaming application. That means the first thing you will need is Apache Spark to submit your Spark jobs. Next, of course, we need a Kafka. And finally, we will need a schema registry. Now, I'm not covering installation in this video, but if you don't have this set up yet, I have dropped link in the description with full step-by-step installation guides. Let's begin with the producer application. The goal here is to produce messages in protobuf format and push them to Kafka. In real-world scenario, this producer could be an order microservices generating new orders, or even a CDC app listening to the changes in orders table and streaming them to Kafka. We are going to build this using Scala and Spark. I'm using IntelliJ, but you can use any ID you are comfortable with. I'm also going to use Scala version 2.12 for compatibility with my Spark version. You can adjust this based on your local setup. So, what do we need to start? First, we need a way to compile and include .proto files into our jar automatically. Sure, we can do this manually, but we will save time by using an SBT plugin instead. So, let's create plugins.sbt file. Inside the project folder and add the required Protobuf plugin. Okay, so it's done now. Now SBT need to know that our .proto file should be bundled with the jar. We will add those instructions to our build.sbt file. Next, we define our dependencies. I usually start by declaring some version variable. Then under library dependencies, we have to add couple of things. The first one that I'm adding here is the dependencies for Spark Core and Spark SQL. Okay, so the next thing that I'm adding is the Kafka Spark integration dependencies. Then I'm adding Protobuf libraries for serialization and deserialization, Confluent libraries for schema registry support, and finally some basic logging dependencies. Once that's in place, we are ready to define our protobuf schema. Let's create a .proto file for our order object. Make sure you create this inside source main protobuf folder. If you place it elsewhere, you will need to configure the path in the build settings. Let's define the order message structure. Okay, it's done. I had already copied it and I have pasted it here. So you can see there are 4 columns in this order structure. First one is the order ID, customer ID, amount and status. For keeping it simple, I have just kept the 4 columns. Okay, so the basic setup of the project has been done. Now let's compile the project and check if everything is working or not. Oh wait, small mistake. I need to put Spark version 3.5.0 and I also need to bump up the Scala version. Let's build it again. And oops, it's plugins.sbt with an S at the end. Let me fix that too. Also, I have forgot to include the SBT assembly plugin. Let's add that as well. Now I will run SBT assembly and see if the .proto files are compiled correctly. Let's wait for some time. I'll see you after build. Yes, this build is successful. If you check the target folder, you will see the generated Scala classes for the protobuf objects. This generated Scala classes includes all the data structure defined in your .proto files, like messages and enums along with methods to serialize, convert to bytes and deserialize read from bytes. They also handles important feature like default values, field validation and compatibility with the protobuf format. So your application can seamlessly send and receive structured data efficiently. Before we proceed further, let's understand protobuf. So what is protobuf really? Protobuf is short form of protocol buffer. It is a language agnostic serialization format developed by Google. It replaces loose unstructured JSON with something far more powerful, a well-defined version contract, something like this. This .proto file is the source of truth. It defines the schema, the exact structure and data types of your Kafka message. From this file, you can auto-generate code for Java, Python, Go, Node.js, Rust and many more other languages. That means producer and consumer in any language can talk to each other safely, efficiently and consistently. Protobuf is faster, smaller and safer than JSON. It's made for real-time, high-scale system. That's why Netflix, Uber and Spotify uses Protobuf across their pipelines. Now you might be thinking, how is the flow? The producer takes the data and serializes it using the .proto definition. It sends a compact binary payload to Kafka. The consumer needs the same .proto file to deserialize that binary back into usable data. This gives us speed and structure, but introduces a new challenge. How does this .proto file get shared across different consumers? How do all consumers stay in sync? What happens if the producer updates the .proto file, but some consumers are still using the old version? In theory, You could put the .proto file in GitHub and tell every team to keep in sync. But in real-world data platform, with dozens of producer and hundreds of consumer, that's a ticking time bomb. If a consumer uses an outdated .proto deserialization breaks, or worse, the data looks fine but it's wrong, so what is the solution? You need a central system that stores every version of your schema, ensures producer and consumer references the correct one, that supports compatibility check before deployment, and allow consumers to dynamically fetch the schema when processing data. That's where Schema Registry comes in. Think of it as a central library of schemas, where every version of every Protobuf schema is stored and versioned. When the producer serializes a message using Protobuf, it registered the .proto schema with a schema registry. The registry returns a unique schema ID. The producer embeds that schema ID along with the binary data in the Kafka message. Now here is the magic. When a consumer, say a Spark structured streaming job, reads the Kafka message, it extracts the schema ID from the message. It contacts the schema registry and asks, hey, give me the .proto for the schema ID 42. The registry returns the exact .proto file. The consumer deserializes the message dynamically with full context. Awesome. Now let's build the actual producer logic.
We start by creating a producer object and usually a main method. This is the entry point of our streaming job.
So step 1, we create a Spark session and read JSON data from our Kafka topic named order.
This is the heart of any Spark job. This import gives us access to Spark's implicit conversion like .age. Now this is where the magic starts. We are reading the streams of data from the Kafka topic order. We are using the Kafka connector provided by Spark.
Right now this data frame contains raw JSON strings. We will parse it into structured format using Spark from JSON.
Since Kafka stores messages as bytes and we are sending JSON, we need to explicitly define the schema. So Spark knows how to parse it. This schema matches the field in our JSON payload like order ID, amount, status, etc. Here we are creating the raw Kafka value as a string. Parsing it using our schema from JSON. And then flattening it out into individual columns. This gives us a clean data frame with each order's detail as typed columns.
Then we will convert each row into an order object using the Protobuf class we generated.
We will convert each parsed row into a protobuf object and serialize it using Confluent Kafka Protobuf Serializer. We use a builder pattern provided by the generated Protobuf class. This creates a typed order object with all fields populated from row.
Next, we create a Kafka Protobuf serializer. This is how we will tell Kafka, hey, I want to serialize orders object using Protobuf. We configure this serializer to point to our schema registry at localhost 8081. This way, it either registers a new schema or reuses an existing one based on the schema footprint. We pass in a Scala map, but Kafka expects a Java one. So we convert it using .addJava method. The second parameter to configure is false, which means we are serializing the message value, not the key. With the serializer ready, we can serialize each order and produce the protobuf encoded message to a new Kafka topic. Serialized order. Once this is done, I convert it into data frame with two columns, key and value. Both are bytes array. Then I am writing this to Kafka using structured streaming. Format is Kafka. I set the bootstrap server, target topic, and the checkpoint location so Spark knows where to resume if something crashes. And that's it. This stream will now keep running and push protobuf messages to Kafka in real time as new rows arrives. Okay, here comes our first break the system challenge. This might seem harmless, but the outcome can be surprisingly unpredictable. So, break the system challenge 1. Here is quick one for you. Try sending message into Kafka without a key. Now think about it. Will the message still get delivered reliably? What happens to partitioning and message order? Will consumer behave differently? Run this test in your setup and let me know in the comments what you discover. Did something unexpected happen? Cool. Now let's build the project and run the producer to test it. Okay, so build is successful. Now let's build the consumer part. Most of the setup is the same, so I will reuse as much as code possible and adjust the logic for consuming.
Alright, let's create a brand new project for our Kafka consumer. This will deserialize the protobuf data we produced earlier and convert it back into the usable Spark data frame. Let's add plugin.sbt inside the project folder. In the plugin.sbt file, we will copy everything from the producer app. Now in the root build.sbt, again we will copy everything from producer app. This ensures all library versions stay consistent. Next, let's create a folder to store our protobuf definition. And I'll copy the order.proto file from the producer application. This order.proto file defines the schema we use to serialize the data. Now let's create the consumer object.
This time we will read from serialized order topic. Inside our Spark app, we select the value column. That's where the protobuf encoded message is stored. We are using map partitions instead of mapping each row individually. This is more efficient for deserialization. Inside each partition, we create a Kafka Protobuf deserializer for order. We configure it just like the serializer, pointing it to Schema Registry and telling it which protobuf type to expect. Then for every row, we get the byte array, deserialize it, and extract the order fields. Order ID, customer ID, amount, and status. Finally, we convert the result into a structured data frame with proper column names. This is your deserialized Spark data. Now we can write this data to another Kafka topic, say JSON order, in JSON format. Let's build and run the consumer application. So before running anything, we need to start all the services. So first one is Zookeeper. Well, it's running now. Then Kafka. Once Kafka is up, we will create our 3 Kafka topics. Okay, Kafka is up now. Let's create the first topic, orders. This is for the raw JSON where we will put our orders data. Let's create the second one, serialized order. And the last one, JSON orders. Okay, the topic creation is done. Now start the schema registry. When we use Protobuf with the registry, we don't need to manually create subjects. It handles schema version and registration automatically. Okay, so schema registry is up. Alright, time to run our application. Okay, running the producer application first. Oops, there is some typo in my select expression. Let's fix it. Build again. Okay, now it built successfully. Okay, running the producer application first. So running the consumer application. It's running fine now. So let's test the whole pipeline. I will produce a test order into the orders topic using Kafka console produce. Then we will check the serialized order topic using console consumer. We should see the protobuf encoded messages. Okay, before that, let's start the producer and consumer. So I'm starting the first producer for the first orders topic, from where we will be producing the orders data. Next, I am starting a console consumer for the serialized order topic. The next, I am starting the console consumer for JSON orders. Now let's produce the data. I'm taking one sample order data and I'm publishing it to the orders topic. Okay, now let's check the serialized order topic. Yes, we see some data here that is serialized. Now let's consume from the JSON orders. Beautiful. We are getting the original JSON structure back. Here is what just happened. We produced an order in JSON format to the orders topic. Our producer app picked it up, converted it to Protobuf, and registered the schema in the schema registry. Then it published the serialized message to serialized order topic. Our consumer picked that up, fetched the schema from the schema registry using the schema ID in the message, deserialized it back into the order, and pushed the result to the JSON orders topic. Alright, time for another break the system challenge. This one is simple, but it catches many off guards. Break the system challenge number 2. Change the data type of a field in your .proto file, like switching float to string. Then rerun your producer, but don't update the consumer. What do you think will happen? Consumer crashes with deserialization error? Consumer silently reads incorrect data? Everything works fine, no issues? Or proto files fails to compile? Give it a shot and tell me your answer in the comments. Or ask if you get stuck. Let's now check what's in the schema registry. I'm using a curl command to list all the subjects. There it is. Our topic's subject name is present. Let's check how many versions exist. Just one. That's expected. Now let's inspect the schema inside version 1. And there you go. This is the exact same schema we defined in our .proto file. When we use Protobuf with Kafka, especially with schema registry, something magical happens behind the scene. Kafka doesn't just blindly send bytes, it sends a very specific structure, so the consumers know exactly how to interpret it. Let me show you what that structure looks like and why schema ID is the key part of it. Every message sent by the Kafka when using schema registry starts with a structure like this. First byte is the magic byte. Next 4 byte is the schema ID. And after that, everything is the actual Protobuf data. So, why do we need this structure? Because the consumer receiving the data has no idea what schema was used until it sees the schema ID. The schema ID tells the consumer exactly which schema version to fetch from the schema registry to decode the message. Every time you register a new Protobuf schema in the schema registry, it assigns a unique integer ID. When the producer serializes the message, the serializer checks if the schema already exists in the registry. If yes, it gets existing ID. If no, it registers the schema and get a new ID. That ID is then embedded into the message right after the magic byte. Have you ever wondered how Kafka consumer know what schema to use without you explicitly sending a .proto file? That's how schema ID message points directly to the schema in the registry. Here you can see the first byte. That's the magic byte. The next 4 byte represents the schema ID in big indent format. Everything after that is a Protobuf data. This is why consumers don't need the .proto file manually. They use that schema ID to fetch the exact schema they need. Back when we said we need a single source of truth for schemas, this is it. The registry takes our .proto file and tracks its version by version. In our consumer code, we created a Kafka Protobuf deserializer and passed it the Schemas registry URL. Behind the scene, the deserializer reads the schema ID from the message, calls the schema registry to fetch the schema, and deserialize the message into a usable order object. That's how Kafka plus schema registry plus protobuf makes producer consumer communication schema safe and language agnostic. Now you might be thinking, wait a minute, if every Kafka consumer has to connect the schema registry every time it receives a message just to get the schema, wouldn't that create a lots of latency? That's a great question. And the answer is no. Thanks to intelligent caching. When a Kafka consumer, like a Spark job or a microservice, receives a message, it first reads the schema ID embedded in the wire format. If it's the first time seeing that schema ID, it reaches out to the schema registry, fetches the schema, and store it in the local cache. For all other subsequent messages with the same schema ID, the consumer simply reuses the cached schema. No network call needed. This means that even in high throughput environment, your consumer only experience a tiny delay on the first message per schema ID. After that, deserialization happens entirely in memory at near zero cost. So far, we have seen how producer serializes data using protobuf, sends it to Kafka, and the consumer deserializes it using the schema from the registry. But in real world system, the schema evolved. New field get added as business grows. Let me show you exactly what happens when the producer changes the schema, but the consumer isn't aware of it yet. Let's go to the .proto file used by the producer and add a new optional field. This new field, payment method, is marked as optional, which is key to maintaining the backward compatibility.
Adding payment method field in the schema. Then setting the payment method to the order object.
Now I'll recompile this .proto file and restart the producer. Okay, it starts producing messages using the new schema, which get registered as a new version under the same subject in the schema registry. But here is the twist. My consumer is still using the old schema. It has no idea that this new field was added. And as expected, the consumer processes the messages without any error. But if you look at the output closely, the payment method field is missing. The consumer is using the older version of the schema, which doesn't include the payment method. Since Protobuf supports backward compatibility, the serializer safely ignores unknown fields. This means your system doesn't break, even if producer evolve faster than consumer, as long as you evolve the schema correctly. Okay, now let's jump into the schema registry REST API and check what happened. I'm using a curl command to list all the subjects. There it is. Our topic subject name is present. Let's check how many versions exist. One new version has been added. That's expected. This confirms the producer registered the updated schema automatically. Schema Registry stores all schema versions under the same subject name, and each one gets a unique schema ID. Now let's inspect the schema inside the version 2. And there you go. The exact schema we changed in our .proto file. Now let's consume a message from the topic and look at the raw wire format using kcat and xxd. Let me run the command. Let's look at our first 5 bytes of the message. 00 is the magic byte, always 0 for schema registry based serialization. The second part here, this is the raw new schema ID in 4 bytes. It's 2. Earlier this value was 1 and now it's 2. This change confirms that the producer is now sending the message using schema version 2. Now I'll update the consumers.proto file to include the new field payment method. Recompile the .proto and restart the consumer. And now the consumer fully understands the new schema. You will see the new field payment method being printed along with the rest. Yes, so here you go. You can see now the field payment method is being propagated. This is how you achieve backward compatibility. This flexibility is critical in modern data system. You can roll out new fields in stages. Old consumer won't break. New consumer can take advantage of richer data. It's safe, versioned and schema driven. Thanks to Protobuf plus Schema Registry. Here is the last one, a bit more advanced, but absolutely worth knowing. It dives deeper into how tools behave differently under the hood. Break the system challenge number 3. In this challenge, switch your Protobuf code generation from the standard Google Protobuf compiler to Scala PB. Generate your order class using Scala PB instead of ProtoC from Google. Rebuild your producer and consumer with the Scala PB generated class. Run the pipeline and observe if serialization and deserialization still seamlessly works. What differences do you notice? Any compatibility issue? Does your pipeline break or keep running smoothly? Try it out and share your experience in the comments. This completes the end-to-end flow, JSON to Protobuf to Kafka to Schema Registry, deserialize back to JSON using Spark. If you are building something similar or stuck anywhere, drop a comment. I'll read and reply to as many as I can. And if you have done Protobuf with Spark before, I would love to hear how you structured your pipeline differently. Hope this gives you a solid foundation on how to use Kafka with Protobuf and Schema Registry in real-time Spark pipeline. This is the modern way to exchange data at scale. Protobuf for structure, performance, and type safety. Schema Registry for dynamic schema resolution and version control. Kafka as the backbone. Consumers like Spark that don't break when things evolve. Before we wrap up, in this demo, I used a statically typed schema in the consumer. That means the .proto file definition was known ahead of the time and the code was generated for it. But there is another way. You can use dynamic message where consumer fetches the schema at runtime from the schema registry and deserializes without any pre-compiled code. So, what is the difference between static and dynamic, and when do we use what? So, static schema, that is generated code, is faster and more type safe. Great for stable pipeline with fixed schema. Easier to integrate with IDs and strict compile time checks. Dynamic schema is more flexible, especially when schema evolve frequently. No need to redeploy consumer for every schema change. Ideal for generic consumer like data sinks, logger, or analytics processor. Each has its own trade-offs. If you want performance and safety, go static. If you want flexibility and decoupling, go dynamic. Now you have seen both the power of Protobuf and control of schema registry. It's your call how deep you want to take this. If you want to explore the code yourself, I have shared the complete implementation on GitHub. You will find the producer, consumer, schema files, and everything you need to try this setup end to end. Link is in the description below. Feel free to clone it and experiment. So, if you are serious about building resilient, scalable Kafka pipelines, Protobuf and Schema Registry are not just nice to have. They are non-negotiable. No more guessing what your message look like. No more silent failure, broken consumer, or debugging nightmares at 2 a.m. Instead, you get fast, compact message with enforced contracts and a centralized system to manage schema evolving without breaking anything. This is how data moves reliably at companies like Netflix, Uber, and Airbnb. And now you can bring the same power to your own pipeline. Protobuf gives you the structure, Schema Registry gives you control. Together they give you peace of mind. If this helped clarify how it all fits together, hit a like and share it with your team. And if you want more real world data engineering deep dives like this, you know what to do. Subscribe to the channel. See you in the next one. Till then, stay curious and keep building cool stuff.